Hello, everyone. I want to continue our discussion about light and talk a little bit more in depth about a couple different things with you. This is going to be a rather short lecture, actually, and then I'm going to continue with the last topic in a third lecture regarding Module 9, and then that should be everything in Module 9. But where we left, one of the things that we left off talking about last time was the intensity of light, and we talked about, what would be harmful to human health and how much power should we worry about. And I gave you this equation that you see here, where you can calculate the intensity as being the power given off by the light source divided by the area over which it spreads out. So I want to use this equation in an example for you so that you can see how one would actually calculate this. So light disperses uniformly in the same sort of way that the electric field might, when we were discussing electric field and Coulomb's law and how things were related to the inverse square of the distance. And so if you take as an example, say a 60-watt light bulb, and you're placing it 3 meters away, then the light is going to spread out over a spherical area with a radius of 3 meters. And so how you would go about calculating that would be to take the power and take the spherical area, 4 pi r squared, and you would divide the power by that, so that you would find an intensity of approximately 0.53 watts per square meter at your location 3 meters away from that light bulb. Now, just like any other inverse square law, if we now double the distance away, say for example we place the light bulb now 6 meters away instead of 3 meters away, I don't even need to go through all of this calculation from scratch to just understand, well, I've gone twice as far away, and since this is an inverse square law, just the same way that Coulomb's law was, I am now going to divide by that twice as far away squared, so I'm going to divide by 4. So that my intensity would now be equal to this 0.053 divided by 4 now for my intensity at 6 meters away. Okay, so that's an example of how you might actually calculate the intensity at your location. Let's do another one that might be relevant to our everyday lives without us even really knowing it, and that is how much intensity do we receive from the sun at the location of the Earth. So some given values are stated in the problem here. We have a power output. This is how much light the sun actually gives off at its source. And then our distance from the sun is given here. So that's approximately 1 AU, or 93 million miles, or in SI units, 1.5 times 10 to the 11 meters. So if I take this equation that the intensity is equal to the power divided by the area through which it spreads, then that's going to give me my 3.9 times 10 to the 26 watts in the numerator divided by the spherical area of 4 pi r squared, where r is this 1.5 times 10 to the 11 meters, all squared. Plugging that into my calculator, I should find that the solar intensity will be something around 1379 watts per square meter. Okay, so 2 examples of how you would work with that equation for intensity to calculate what the intensity of a light source is at your location. The point being that the intensity does drop off as a distance, an inverse square law of the distance squared. So, the farther away we get away from light sources, the brightness drops off relatively quickly, which is why raging infernos of stars that are the size of the sun, or many of them much larger than the sun, just appear as tiny little pinpricks of light in our night sky because they are located so far away. Okay, so another thing that light can do, switching topics here, is that if a light source is moving, it can exhibit a Doppler effect. You're probably more familiar with Doppler effects as it applies to sound. If you're standing out on the sidewalk and you're listening as an ambulance is blaring its sirens and drives past you, you will hear that the pitch of the siren sounds higher in pitch as it's approaching you and then lower in pitch as it moves away from you. This Doppler effect is exhibited with light as well. And that may seem absurd on the surface because when that ambulance passes you and you see the lights of the siren going off, you don't see a change of frequency of the light, right? You don't see it change color as it's approaching you and receding away from you. And the reason for that is that it's much easier to notice a Doppler effect as it applies to sound in our everyday life than it is to notice a Doppler effect as it applies to light in our everyday lives, because the speed of light is much, much faster than the speed of sound. And to actually get an appreciable effect would require that the object would be moving at a high rate of speed. As we'll see in the equation on the next page, that doesn't really amount to a huge Doppler effect for light at everyday speeds that we might be familiar with. So the equation for calculating the frequency that you observe based on the relative speed between two objects is given by this equation here. So this equation is essentially going to be the same equation you would use for sound, except that we would replace this speed of light c with the speed of sound. So you can see that it's a ratio of the relative speed of the two objects divided by the speed of the actual wave, which in this case we're talking about light, but for sound it would be a much smaller number here, so it would be easier to get a value here that when you subtract it from 1 or add it to 1 will give you something to multiply by the frequency given off by the source that you can actually detect. For light, you need a very high relative speed for you to see any kind of effect. So let's take an example. Let's say f sub s is the frequency given off by the source. So let's suggest that there's a light source that's giving off a frequency of 5,000 hertz. Okay, and let's say that it is moving with respect to maybe the Earth at a relative speed of 3,000 meters per second. Now, I want to know how much of a Doppler effect I can expect to see in the frequency that I observed based on this equation. Now, I've got to decide, do I want to use the plus sign or the minus sign? So to reason through this, you've got to ask yourself, okay, well, if it's moving towards me, do I expect the observed frequency to be higher or lower? And away from me, should it be higher or lower? If it's moving towards me, let's go back to the previous slide for a second. If it's moving towards me, then as it's giving off these waves, it's sort of scrunching the waves in the process, and they are becoming higher and higher frequency in its motion towards me. We would call this, by the way, a blue shift in astronomer jargon. And on the contrary, when it's moving away from me, these light waves have a chance to spread out, and the frequency becomes less and less, and it's shifted towards the red end of the spectrum, so I would call this a red shift. So going back to our example then, if I expect the frequency to be higher when it's moving towards me, then that means I want to add on, I want to add on to the frequency, multiply the frequency by something greater than 1, right? So this plus sign is going to be for motion towards. And the minus sign then will be for motion away, because in that case I expect a lower frequency, and so I want to subtract from 1, so I'm multiplying this frequency giving off by the source by something less than 1, and I'm making it a lower frequency as a result. Okay, so let's say that this particular light source is moving towards us. So I'm going to choose the plus sign there in the formula. So the observed frequency I would find then for this example would be the frequency given off by the source, which was 5,000 hertz, times 1 plus 3,000 meters per second over 3 times 10 to the 8 meters per second. So plugging that into my calculator, what I will find is that the observed frequency will be 5,000.05 hertz. Okay, and you could reason that if it were moving away, I would just be subtracting this small little fraction from 1, and I would find an observed frequency of 4,999.95 hertz. So the question is this a change of frequency that I could detect as a color change? Likely not. And, this is why we don't see it in our everyday lives, because ambulances are definitely not moving at 3,000 meters per second, and nor are most things that we encounter in everyday life. Out there in space, there could be objects moving at such a high rate of speed or even higher. And yet the question again is, well, still, am I going to see this as a frequency change that's appreciable enough to notice by eye? The answer to that is no. So how do we actually measure the Doppler effect? How do we even know that it's happening? What astronomers generally do is they look at the spectrum of the starlight that they receive. And buried within the spectrum is information that they can use to determine what this Doppler effect is and to measure this effect. So if you were, say, in a lab or a setting that was at rest, you might notice two double lines in orange that correspond to, say, sodium. Maybe this is your sodium doublet. And you know very well exactly where this frequency is for each line when you're sitting still in a lab. So if you receive some starlight and you see the same pattern of double lines, but they are just shifted, so you know this is sodium again, but it's just a little bit shifted to a higher frequency than you expect, then you can say that that must have happened due to this Doppler effect, due to the motion of the star. Likewise, if these two lines are, say, shifted in the other direction towards the bluer end of the spectrum, then you can tell that that motion must also be there, and it must be moving towards you in this case, or away from you in that case. So the point is that whenever a Doppler effect is occurring with light, you don't actually generally see this as a color change, but it can be detected by very precise measurements of the location, the frequency location of different shifts in, say, a star or galaxy's spectrum. Okay, so the final phenomenon with regard to light that we're going to discuss today, and we're going to go into more detail on the next lecture, is polarization. So whenever light is given off, it's generally what we would call unpolarized, whereby these vectors could indicate a sort of random orientation of, for example, your electric field. We talked about how the electric field will be mutually perpendicular with the magnetic field oscillation, but let's just, for simplicity, look at all of these vectors as depicting the direction of the electric field for a given light source. So they kind of are given off in very randomized ways, in which this could point in just sort of any random direction, and we would call that unpolarized light. As the light propagates through space, if it enters something that we would call a polarizer, then for example, your sunglasses may be polarized, and this could be an example of a polarizer. And there's other such filters, polarizing filters. When it comes out on the other side, effectively it will be what we call linearly polarized, and the intensity that we receive on the other side is only half of what it was to start with. And we can talk about the mathematics of why that is perhaps in the next lecture. But suffice to say for now that this unpolarized light, as it passes through the filter, will emerge with a specific orientation where all of the electric field vectors or lines. Actually, all the electric field oscillation is taking place in a way that aligns to the arrows that you see here, and we would call that linearly polarized. And the intensity of all of that light is now reduced to half of what it was before. Okay, then we can further put another polarizer in here, which is usually called an analyzer. And this law here, Malice's law, tells us then that if we have this linearly polarized light going through yet another polarizer, when it emerges from this other polarizer, the intensity will drop off according to this equation here, where if I take the intensity of the linearly polarized light, so this is not the original intensity, this is the intensity, of the linearly polarized light, then that intensity will be reduced by the cosine squared of the angle between the direction that it is polarized in and the orientation of the second polarizer. So we're going to talk a lot more about Malice's law in the next lecture, but I just wanted to introduce it to you briefly in this one. All right, thanks, and I will talk to you again.